Okay, now as we are going to start to set up the system to study this slab and to find the surface properties. One of the things is the passivation. So I'm going to the surface. So I'm going to show you one of these, right? So I'm going to show you this postcard. I'm going to show you this. Look this. This structure is this. You see? It has only one atom and the last layer has only one atom in this unit cell. See? And then it has other atoms. So these two atoms, you see how many? It is only two coordinates, right? And these are surface atoms, right? The problem is that these blanding bonds are very active. So if for a real surface, yes, we leave it like it because will be these dangling bonds will be very active and we can make reactions. But this one I want the electrons here to believe that here is perfectly listen. Therefore, this if I want this to be bulk-like, I have to passivate. Okay, so how we passivate it is we're going to put two hydrogens and we passivate the silicon. Okay. And that's it. So that's why, and after that, we're going to see for relativation, we fix this and we will see what we're doing. So the first step is describing an analysis. And we are going to, first of all, I'm going to teach you how to passivate this, how to add two hydrogen atoms here. And then we are going to proceed two relaxations, right? First relaxation, we fix everything, including this last silicon, and we allow to the hydrogen to find equilibrium position, right? Why? Because we want also the hydrogen to emulate this perfect, yes, the perfect bonds between silicon. After this, the next step is and that's it, right? So once we have this, after that we fix this silicon with the two hydrogen, and we allow system to relax to find the atomic structure of the two. So that's the way of the we find the as you can see, when in this simulation, we talk about surface. See, surface is not what to be, it is in fact 3D. Because the properties of surface is related with the relaxation of the that's the reason why surface, the concept of surface is more complicated, more let's say, has more elements than the typical idea of pieces. Okay, so let's go ahead, please. So the first thing is that you see it asks you we're going to passivate. For that, please, we're going to transform this postcard one by one. By the way, the notation by one by one. Yes, correct. So we have notation to see here is the one by one. So if one by one is this, right? One by one, what I got, this is the cross section I got directly when I cut the crystal in the unit set. See? So there is other kind of supercells, let's say, or the geometries of the lattice will be like this. This will be 2 by 1, see? And this will be 2 by 2. See? So if we do this, and this, and we found that the most, let's suppose when you find the literature of those surfaces, they tell you about the construction 2 by 2, 2 by 1. It means that despite all of the, when you have the user, you have this, and you put this. If this has lower energy than this, you know that this is the ground state. So the ground construction of this surface will be 2 by 1. Could be also 2 by 2, etc. So it depends. So you have to perfect the construction and so on and so forth. Sometimes you believe that make it will be a 2 by 2, so you create a 2 by 2 cluster. When after relaxation, by relaxation, you get back the 1 by 1 by symmetry. You see? So we everything these details we are going to check, during this hands-on session. So first thing is that we are going to manipulate with Material Studio this structure. Why this 11? So it has 11 natural vacuum because I'm going to passivate this, so I will take out one later one Armstrong for the other. So I will be left with 10 Armstrongs. Remember, I need at least 8 Armstrongs to have convergence. So we'll do 2 more to establish this. Okay, so let's do this. So let's transform this to postcard file. This post, so just you can copy from this, and it's right. There it is. Okay, so I have the zip file. Now this, I'm going to read this zip file and do the following, right? So here it is my Material Studio. And I'm going to import here. So I'm going to show you how to import this. So I'm going to import this. You know already how to import anyways. So here is the icon, this icon here, this with this yellow folder here. Import says import, right? I'm going to import this surf, this postcard. Where is this? What is my? I was thinking I was creating this. What is this? Okay. Second byte. Postcard 11, 11 point, is 11.0, sorry guys, it's 11.0, 0.init, right? We want to transform this 11.0.init, this one, okay? There it is. So in this there is a mistake, it's 11.0.init, okay? So we have this, now we are going to import this, please. Cancel, okay. So I open this folder and here it has to be the 11 point. Here it is, slab this. So there you go. There it is. Please, everyone till here, please. I'm going to pause this. Okay, so in this case, as you can see, you put bonds in the system, and after you want to see the atoms as spheres and sticks. There it is. There it is. Look, I have my structure. Oh, sorry. Look this. In this case, look, there is this atom appears here. So this is the image of this. If you want to get rid of this, you can put this, you put this style, this display style, and you put lattice, and you put incel, and sorry, you put original, and that's it. That is the original atoms in my system, okay? So in that case, there is no atoms here because you have only the originals. Okay, so now what is next, please, is we're going to do is the following, please. Please, you have to be careful with this, please. With the arrows here, rotate the structure like this. You see? It has to be perfectly aligned, you see here. Because if you do like this, only like this, it will fail what we're going to do. So please do it exactly. Why? Because right now we are going to move the structure 1 Armstrong up. Okay. Next, select this. So you see, choose this icon here, the white icon, and we're going to select the structure, right? And now we're going to move this, right? So you see there is an icon called movement, this icon here with movement. And after you're going to put the distance of, you see, I just selected here the distance of 1 Armstrong going up. See? There it is. I repeat again, please. I'm going to repeat again this. One second. I'm going to pause here. Okay. Now you did this. Please select this the the lowest silicon atom and press the H, please. This one. And automatically you're going to have the two hydrogens. I repeat again. When you already move this, you want to passivate this silicon atom. So what you do is to select this and to press H. With this material field, will put the two hydrogen atoms to passivate this silicon atom. I'm going to pause here. Okay, so once we have this structure, we have to save it to do the calculation we need. Okay, so we're going to save this structure as a slab. Look this. We are going to. It says save it as a slab SEHB10.zip. So I'm going to save the file, export, right here. I'm going to copy this. I hope it's working. Let's see. Like this. Yes, you see? So I save it as a slab -SIH-B10.zip. And you have to save it as a C file right here, crystallographic information. Save it. That's it. So now what I have to do is to bring that file, this C file, to my computer and to read. So I'm going to, in this case, I have to, unfortunately, okay, I'm going to pause here, okay? Okay, so now I saved the file and I have my folder here, this file, so I'm going to open with us. It's for the okay. See? And this, and what happened? No. Secure. Okay, something happened, so let me see. I have to find that this here. Yes, it's here. So I'm going to open it with us. Right, so I'll see. There it is. Okay. So there is my file, which you can see here. So before I start to do anything, the first step is to freeze everything and just allow to relax the hydrogen atoms in such a way that the hydrogen atoms look up and they see a perfect crystal structure of the silicon. So I select, look this, I select all these atoms here. See? And you come to tools, you go to constraints, and you say fix it. Repeat again, please. Okay, I'm going to pause this. Okay, repeat again, please. So once you have these atoms, I want to fix everything here, except these hydrogen atoms. You come here to tools, constraints, and you fix this. When it's fixed, appear an X over here. That's it, right? So that is the structure. We're going to relax, but the only thing is going to be relaxed is these hydrogen atoms. Okay, so we are going to find this optimal structure or optimal geometry of the hydrogen atoms that are passivating to the silicon atom. Therefore, we are going to save this as a postcard 1x1 L5 B10. Okay, so let's save it. This file, save as like this. Okay, we're going to save it like this and press Enter. Okay, if everything is fine, you have already this postcard. You can visualize this postcard. Let me see. Yes. So there is the file, please. Like this, and there is this, and there it is, right? You have silicon, you see the order, silicon and hydrogen. So you have 5 silicons and 2 hydrogens. That is the order you have. And you see here, you have F and you have T. F is that we can interpret as everything is fixed, right? And T means that is non-fixed. It is these atoms are allowed to move. In this case, these two atoms that has T are the hydrogen. Okay. Anyways, I will stop the process here. Okay, so I'm going to do two types of relaxations. Why? Because if you see the structure, I'm going to do as if you see this structure, you are going to see that this, if we perform a relaxation in this Postcard file, in this structure, it means that everything will be fixed except the hydrogen atoms. So the hydrogen atoms are going to move, like have to arrange themselves in such a way that they lower the energy of the system. Why we do this with fixed other atoms? Because we want to emulate the perfect like crystal above the hydrogen atom. So the hydrogen will believe that they are, when they look upwards, there is a perfect crystal. Okay, so that's the way to emulate and passivate these kind of atoms at the bottom of the surface. Okay, so that's it. So we're going to do this relaxation where only hydrogens will move. And what else? What we are going to do? We are going to propose that we need a Postcard file in my calculations, right? So therefore, since the Postcard file has this, what is my Postcard file? Sorry, where's it? No, this is not. This is not. I'm going to open my Postcard file, please. This one. As you can see in this Postcard file, silicon is first and hydrogen next, right? So my Postcard file has to have the same information of these atoms in that order. For that reason, first of all, let's see if I have here in the back. Let's go to the back, and we're going to join this this pseudo potential. So for that, do this. And the hydrogen file, we're going to like this. Vodka hyphen A. The manual says that let's put it like SAH, SAE hyphen H. Okay, so there it is. We have the podcast file. Yes. Yes. So in case we have the podcast file, right? What else we need to? Okay, so we have the podcast file. Because we have two species, we have to combine the podcast file in this way. Okay. So this is here I show you how to transform this, how to join the two podcast files. Okay. What else? We need we're going to perform an ab initio calculations. Why ab initio? Because in this case, since we will have hydrogen in my system, the force field won't understand, what these atoms are there. That's the reason it's not possible to use force fields in this case. So I'm going to use we're going to do a relaxation using ab initio, right? Only ab initio. Okay. We are going to use the same separation that we use. Remember, this delta K is equivalent to 771. And we are going to do this initial relaxation, okay? So we are going to run this RXO. Where is this? So we are going to run this. We are going to run this script. This script will help me to relax the hydrogen atoms in the perfect slab. We are not going to allow this at this moment to relax the slab. Okay. So basically, what I have to do is okay. So I need yes the postcard file. Yes, I need the K.1 and this. Okay. So I have everything. So in this case, what you have to do is we have to copy this script inside of this folder. Okay. So let's copy this inside of this folder. Okay. We are going to run this XRO, this extra row, I'm going to edit this course. You don't have to do this, just I do it to be to run and to check how long does it take also. And here, you see, this is the level we are going to have for the first calculation. For this calculation will be 1 by 1 L5 B10. So it has to exist the postcard hyphen 111 LB10, right? And this is here, this one, in the same directory. Good. What else? It's going to take the Incar file from the RX from the previous calculations, you see, parallel. So I have to have this Incar file here, RX. There it is. It has the poll corrections, is correct, and so on. What else? The K points by one. Here it is. And what is the K points one by one? K points one by one. There is no K points by one. So we have to create these K points by one. So please, maybe we can copy this. Okay, so please copy these points. So I'm going to do it here. If you like, you can do it by, in the graphical interface. I'm going to copy this because there is no K points one by one. And I'm going to paste here and I'm going to name it K points one by one. Now, in my calculations, remember there was this, when we computed the bulk structure on silicon, we used the 999 grid. Remember this? For the bulk with ab initio. So the 9 by 9 by 9 do here, where is this grids here? The grid 9 by 9 by 9, it was 0.035. This is for the ab initio, please. Therefore, I have to keep the same parameter for the surface. Here's the structure of the slab, right? The 011, the 11100, and this is 0.005 will means that will be 7. It should be 2, but we are going to put 1 because we want perhaps in the C direction. So let's edit please this K points 1 by 1. Okay, and we're going to put 771. That's it. Control S. Okay. This is exactly the name of the file is exactly the name of the file that is called here. You see, cap points 1 by 1 is this one. What else? We have you see, we're going to copy from the directory below the podcast file is I-H to podcast. So it has the same order of this structure. First of all, the silicon and next the hydrogen. And that's it. And we are able to run. So everything is ready. Please check that you have the cap points hyphen 1 by 1 in the original folder, in this part here. No inside of the DFT PC, the ML or Surface. That's to be in this folder in part 8ML. Here outside we have this. Sorry, inside we have this, as you can see. So we have to have this podcast file, this SCH. We have to have this. We have to have the podcast file, right? What else you have to have? Let me see the script. You have to have the Incar file RX. You see, we have to have this. In Incar file RX, check that you have this ILDPOL, right? 3. Very important. Otherwise, there will be a problem. And that's it. The cutoff energy, this is the same. Ready? I think it's ready to run. Okay. I'm going to go inside. Extra. Okay, so I'm going to run like this. This is the script I'm going to run. Remember that this is a script I copied inside of the folder surf and I edited a little bit. Okay, so we are ready to run. So the only thing we need the podcast file and that's it. Okay, let's run. Let's do this. Go to the this. We're going to run this X O. We're going to run this. Okay. You have everything. Sorry. This air XO. Sorry. So now running. So I'm going to pause this here. And this is. Okay, so the result of this calculation was saved, for instance, the outcome file was saved in this outcome file, where this level is here, 1 by 1 and 5v10. So, and the concat file also was saved this. Let's see this output files, okay? I'm going to check this output. Look this. This is the outcome file. Look this. So let's open this. Look this. This is the outcome file that we get. Okay. So here then, as I mentioned, after a correct relaxation will appear this kind of this warning, right? So so this is the first. Okay, after we finish the whole relaxation, look, this is what's going to happen. Look, we go to the end. Oh, we're going to that, and here appears, you see, reach require accuracy, stopping and structural relaxation, energy minimization. Okay, so what was the structure we generate? It generates this. This versus this. I'm going to check the other one. Let's see if the difference between the previous structure and this. This was Postcard L5. Look this. We have this structure. This is the relaxed structure, and this is the, what is this? Let's, what is this? Here it is. Okay. So you see, this is the structure non-relaxed. Okay, there are two. And the relaxed structure. I don't know what happened with this. Anyways, okay. Let's see. 1 second. There is some problem with my. Okay, so as you can see here is the side by side the concat file that we computed. This is the relax. On the right is the relaxed structure, and on the left is the original structure. So this is the one that we created in Material Studio. Look this. So let's check the distance between the hydrogen atom and the silicon is around 1.54 angstroms. In this case, let's see, after relaxation, on the hydrogen, we have 1.48 angstroms, right? And also look the angle, right? The angle is also different. So original was 109 degrees, and now is this, right? 102 degrees. So you see, as I mentioned, these hydrogen were allowed to relax by the appearance. And in that way, we'll passivate efficiently this structure. So the hydrogen might think that this is a perfect crystal structure. So there's not passivate. Now the next step is we're going to fix these two, and we are going to allow to relax all the crystal. So let's see this. Okay. So right now we are going to the second step. So we are in this kind of systems, we are always do 2 steps of relaxation. First relaxation is we allow to relax only the passive, the passive agent. And next, we fix these hydrogen atoms on the first layer, the bottom layer of silicon, and allow to relax the rest of that. Well, if we do this, we trying to give information about the perfect crystal structure of silicon below this surface. That's the, that's the reason why we have silicon. Okay, questions here, somebody please. Somebody has any? Okay, so after this calculation, what we got, the one of the results is the relaxed structure only on the hydrogen atoms. Here is a visualization that we already did. Here is with Material Studio, and here is with ACE. And now we are going to you are going to use ACE to constrain only the hydrogen and this silicon atom, and the rest will be free, right? So we are going to do this. We're going to create this, and we are going to save it as this, postcard 1 by 1 bitten hyphen init dot postcard. Okay, so let's do this. So since I open already this, I close this, and the concar file is in this file, see, the concar file, I'm going to increase even more that you, so you can see what I'm going to do. So we are going to manipulate or to lift to allow the atoms to move. So in that case, I'm going to allow these atoms, I'm going to unfix this. So let's unfix or release this. And I'm going to fix this hydrogen atom. There it is. So in that case, we're going to have this. Okay, I'm going to pause this. So it means that now I'm going to do the relaxation that matters to me, that we're going to find how I should relax the atoms at the surface to lower the total energy. Okay, meanwhile, I fix this, these structures, this atom here in this. Okay, so I'm going to pause this here. So please, open to edit the concar file hyphen to make it work, please, because in some cases, ASA is not possible, it cannot open because of this. Here you have to have like this, no like high, silicon high. There is everything, I'm just needed silicon and hydrogen. And same, that will be. Okay, so you have, please save it, and now you should be able to open. Wait here. So I'm going to do again. I'm going to open this Concar. So if you have a problem opening Concar, this Concar file, please fix this, the labeling of these atoms. Once you fix it, you should be able to open. So I'm going to open. I'm going to edit, please. So what kind of edition I'm going to do? Please, attention. I'm going to unfix all these atoms. So you can hear tools, constraints, and you just say release. And I'm going to fix this atom. Tools, constraints, fix. So the final structure should look like this. Okay, I'm going to pause here. Once you have this, please, we're going to save this file with this name, please. Postcard. What is this? This postcard hyphen dot postcard, like this. Okay, we're going to save it like this. Postcard hyphen 1 by 1 L5B10 hyphen init dot postcard. Okay, so I'm going to file like this, file, save like this. Control B. You see? There is a name. Postcard iPhone 1 L5B10 init dot postcard. Okay, there it is. Okay, so right now what as I'm going to do is to expand this in this direction, this structure. So how to do this? In tools, you have this where is this view, this repeat. In view, repeat, okay? And you're going to put 2 by 2. Repeat again, please. So you take this structure, you view in view, and you put repeat. And you are going to put 2 by 2. You see, this is a structure we are going to actually to consider to find the optimal surface structure of silicon. We're going to set the unit cell, you see. That's it. Okay. So this is my initial structure. Okay. And so on. So this structure we are going to investigate and to find the structure that is observed experimentally, and after that, of course, we're going to generate the STM image. Okay, I'm going to pause here.